Hello बच्चों, welcome to lecture 4 of the number theory series. Here we are going to discuss one of the basic fundamental theorem of number theory. It's the fundamental theorem of arithmetic. Now if you have watched my previous lectures, there is something that I already have discussed about, that is this fundamental theorem. But what we are going to do here, we are going to discuss some of the further questions which is of vital importance for understanding proper sequencing of number theories. So let's straight to the statement of the theorem. So basically what is the statement which we have already discussed earlier. So please watch my earlier lectures to get a proper understanding of this. Now the statement says that every integer greater than 1 is either prime or can be written as product of primes, and this prime factorization is unique except in the orders which they occur, okay, which they occur. Done. Now so statement is clear. Matlab it means for example, if I take every composite number, what is composite number? Numbers which are not prime numbers, actually numbers which have more than 2 prime factors. For example, 6, it has 1, 2, 3 and 6 as one of the factors, but 7 is a prime number because it has only 1 and 7 as a prime factor. 1 is not a prime number. Okay, these are the things that you must clearly understand. Now so there are two things that we have to do here. So let's get a simple proof for it, this statement. So basically what does proof says? Proof, we are required to do two things. First, existence, and second, we can talk about uniqueness. As we have told, this prime factorization is unique except in the orders which they occur. Matlab orders can vary, okay, but prime factorization will be unique. So what do we mean by existence? Existence means any integer greater than 1 is either prime or can be factorized as product of primes. That is about the existence. That is what we are required to prove, product of primes. And what is the second thing? That is uniqueness. What do we mean by uniqueness? I said ki each prime factorization will be unique. Each prime factorization is unique except what? Except orders. Leave aside the orders and everything is all fine. Matlab there are two things that we are required to do. Pehla, existence, and second, we can talk about uniqueness. Okay, so let's see. We can say, suppose let n be any number greater than 1. Okay, that's greater than 1. So if n is greater than 1, then n can be written as p1 per power alpha 1, p2 per power alpha 2, p3 per power alpha 3, and so on, pk per power alpha k. What is p1, p2? p1, p2, pn, pk are distinct prime numbers, are distinct primes. And what is alpha 1, alpha 2, alpha 3? Alpha 1, alpha 2, alpha k are positive integers. are मतलब ऐसे लिख लो, this belongs to set of z plus representing how many times each prime occurs. How many times each prime factor occurs? Each prime factor occurs. That is the meaning of this power. For example, if you didn't understand, I can tell you, say 36. So 36 can be written as primes 9 into 4, that is 2 chi square into 3 chi square. So let's say P1 is equal to 2, P2 is equal to 3. What is alpha 1? Alpha 1 is equal to 2, alpha 2 is equal to 2. So this is about 36. Now we cannot express 36 as another prime factors. It cannot be written like this. Okay. So now for the provens, what we can do simple thing. As I have already stated, कि any factor greater than 1, not factor, any number greater than 1 can be written as product of primes. So let's say what we can assume, assume there exists one integer, मान लो x greater than 1, x belonging to z, that cannot be written as product of primes, that cannot be written as product of primes. Okay, so this is there. Now, so next what we can do, say if such numbers exist, so what we can say, there must be some smallest one, there must be a smallest one. If this type of number exists which cannot be written as a product of primes, so there might be a series of numbers, let's say x1, x2, x3, x4, xn, but we can say there must be some smallest one. Okay, so let s be the smallest one. So let's say s is the smallest one. Now what can we say about s? About s we can say s is not prime. S is not prime. Why? Because if s will be prime, so it can be written as, if s was prime, so it can be written as product of 1 prime. It can be written as product of 1 prime, which we don't want. Why? Because our assumption is that there must be some s which cannot be written down as a product of primes. Okay, done. So if s is not prime, s must be composite. S must be composite. Why? Because every integer is either prime or composite. So it means therefore s must be written as s is equal to a into b, where a is greater than 1 but less than s, b is greater than 1 but less than s. True? Now there is a problem. What's the problem? A and b becomes smaller than s, becomes smaller wait, yeah, it becomes smaller than s. So which is true or not? No, it is not true. Why? Because we say it was assumed that s is smallest and cannot be factored, so it means proved. First part is proved. So first part is proved, first is done, matlab existence proved. Now we will talk of uniqueness. Let's talk of uniqueness. So how can we prove that this will be unique? So let's say uniqueness is proved assuming two things. Suppose n is there, n can be written as p1, p2 and pn. Again, and n, let's say, can also be written as q1, q2 till qn. Qn. Now what we are assuming, that same n can be written as product of two different prime factors. So n, assuming n is written as product of two different primes, that is p's and q's, अलग अलग p के लिए, so अलग अलग सेट ऑफ प्राइम्स बनाया गया है. चेक. Now what is the way to prove it? We can prove, we can say we choose p1, and if we prove that it is equal to q1, then it can be done. Yeah, this is the statement. If I choose any of the p1 from set of p's, and if I choose any of the q1 from set of q's, and if I prove that some p1 is equal to q1, so it's proved. Now how do we do this? Say, do you remember this बच्चों, Euclid's lemma? So what does Euclid's lemma state? अच्छा, एक बात मैं यहाँ पे बोल दूँ, ठीक है, कि एज्यूम मैंने क्या करा है कि n इज रिटन एज प्रोडक्ट ऑफ टू डिफरेंट प्राइम्स, और यहाँ पे मैं मान क्या रहा हूँ, एक्चुअली प्रूव बाय कॉन्ट्राडिक्शन कर रहा हूँ. क्या प्रूव बाय कॉन्ट्राडिक्शन करूँगा? एकदम सिंपल सी बात है. सी दैट इफ n is written as product of two different primes, so let smallest integer is n. Let smallest integer is n, that can be written as product of two different primes. That is what we have taken, matlab we have assumed that n is the smallest integer, that n is written as product of two different primes. Now if I can prove that there is some another integer n dash which is smaller than n can be written as product of two different primes, then our assumption is wrong. That is what we are required to prove. So by Euclid's division lemma, we know one thing. What? Ki if prime number p divides product of two numbers ab, then p must divide a or p must divide b. P must divide b. Okay, p either divides a or p either divides b. Done. So here we are saying, let's say n was written, n prime factor, say choose p1. Okay, also n is equal to q1, q2 till qm. Oh, one was m, another was n. Okay, qn. Okay, so it means p1 must be equal to, must be dividing q1, q2 till qn. But remember one thing, if again by Euclid's division there is one conclusion. What does Euclid's division conclude? One thing it concludes, that if a prime divides a product of primes, then there is one thing that can be concluded. It must be equal to one of those primes. It must be equal to one of those primes. Okay, so if it is one of equal to these primes, then we can choose any one of them. Say, let's say p1 is equal to q1. Then what can we do? It was written n is equal to p1, p2 till pm is equal to q1, q2 till qn. So we can cancel p1 and q1. Why? Because they are positive and they are equal. So if I cancel, say, now it becomes n dash. Why? Because n dash is written as n by p1, or you can say n by q1. So if this is cancelled, let's say n dash, then it will be equal to p2 pm till Pm is equal to Q2 till Qn, which is smaller than n. Now, what was our assumption? Our assumption was smallest integer is n. But what we proved? That there is another n dash that is smaller than n and can be written as product of two different primes. But this is wrong. Our assumption was wrong. So therefore, our assumption is false. And hence prime factorization of any integer greater than 1 is unique. Greater than 1 is unique. That is the statement. Done. Now, but what are the applications? So let's move on to applications and questions. So first simple application is finding HCF and LCM. This is one of the beautiful thing that we can do from fundamental theorem of arithmetic. For example, let's say we are required to do LCM of 120 and 90. Suppose that is what we are required to find out, and HCF and LCM. So 120 can be written as product of prime factors. How? See, 15 into 8 is 120. So 2 cube into 3 into 5. It can be written like this. Again 90, 15 into 6. So this can be written as 9 into 10. So 2 into 3 ka square into 5. Done. Now what is HCF? HCF is highest common factors. It means we can choose lowest powers of common prime factors. Now what are the common prime factors? One is 2, another is 3. So choose the lowest power. So for lowest power, it can be 2 per power 1 into 3 per power 1. Nothing else. Yeah, there is 5 also. So 5. So what is there? So therefore HCF will be equal to 2 into 3 into 5 per power 1. That is equal to 30. Done. Super. Now to find LCM. So LCM, highest powers of all prime factors. So for LCM we can say, suppose there is 2. So the maximum power is 2 cube. Again for 3 it is 2 and there is 5. So 8 into 9, 72, 72 into 5, that is 360. Done. So we found out HCF and LCM using the fundamental theorem of arithmetic. Again, sometimes in other applications, sometimes the question is asked, for example, can the number, and this is common question in CBSE also, can the number 6 to the power n, where n belongs to z plus, end with digit 0, true or false? Can it be done? So how do you do it? First, digit 0. For digit 0, so a number can only end with digit 0 if it is divisible by 10. If it is divisible by 10. True or false? True. Now, but prime factorization of 10, of 10, it has 2 into 5. So prime factorization of 10 is equal to 2 into 5. Now let's see about 6 to the power n. So 6 to the power n is 2 into 3 per power n, which is 2 to the power n, 3 to the power n. Now we know that from fundamental theorem of arithmetic, what do we know? We know that this prime factorization is unique. So from fundamental theorem of arithmetic, what do we know? Prime factorization of any number is unique. Okay. Now it means 6 to the power n contains only powers of 2 and 3. Powers of 2 and 3. So there is no 5. So therefore 6 to the power n contains no prime factor 5 and hence it cannot end with 0. It cannot end with digit 0. Okay? Done. Now again, let's see some of the questions. So application is means digit based problems can be there, HCF and LCM can be there. So let's see some of the question. Question number 1 says let n is equal to 12 per power 3, 15 per power 4, 20 का square. Question says how many positive integers are divisors of n? How many positive integers are divisors of n? So how do we proceed? Now what's the way out? See, we have already studied permutation combination, so I will surely be using that, but we can do certainly one thing. First 12, find the prime factors. मतलब what we are going to do? First prime factorize it. मतलब write n as a product of prime factors. So my first objective will be write n as product of primes. So I'll directly write it. Instead of writing individually, I'll write n is equal to 12 can be written as 2 ka square into 3 per power 3. 15 can be written as 3 into 5 per power 4. 20 can be written as 2 ka square into 5 per power 2. So basically this will be 2 to the power 6 or 2 to the power 4. So 2 to the power 10. Now 3 to the power 3, 3 to the power 4. So this will be 3 to the power 7. Again 5 to the power 4, 5 to the power 2. So it will be 5 to the power 6. Done. So 2 to the power 10 into 3 to the power 7 into 5 to the power 6. Done. Now these are prime factors. Done. Now they say how many positive integers are divisors of n. So basically what do we do? For example, if there is 36, so how do we write it as 4 into 9, 2 ka square into 3 ka square. So what are the ways of making number of divisors? So see, if I am choosing divisor, it must be factors of 36. That is what we are required. So what are the number of ways in which we can choose 2 to the power 2? Either we can choose 2 to the power 0, 2 to the power 1, 2 to the power 2, 3 to the power 0, 3 to the power 1, 3 to the power 2. So choose any of the way. There are three ways. Choose any of the ways and multiply. So 3 ways for 2, 3 ways for 3, total 9 ways. So I can say there are 9 divisors. If you want to verify, let's verify. 36, 1 is there, 2 is there, 3 is there, 4 is there, 6, 9 is there, 12 is there, 18 is there, 36 is there. Did we get 9? Superb. 3, 6, 9. Superb. It means this is the correct way. So again, so divisors of n can be written as, so say यहाँ पे 2 to the power a, 3 to the power b, 5 to the power c. So how many ways can we choose this? So we can choose a plus 1 times into b plus 1 times into c plus 1 time. Why? Because 2 to the power 0 can also be included because it is equal to 1. So therefore 11 choices for 2 into 8 choices for 3 and 7 choices for 5. Done. So basically this will be equal to 11 into 8 into 7. So this is 56 into 11. So 56 into 11 will be 616 and done. So 616 positive divisors of n. Superb. Next question says, question number 2. So it says let n be a positive integer. Such that n square is a perfect cube. And n cube is a perfect square. Find the smallest such n that is greater than 1. So please read the question carefully. Let n be a positive integer. such that n square is a perfect cube. Superb. And n cube is a perfect square. Superb. Find the smallest such n which is greater than 1. Now how do we proceed? What is the way? See, n is a positive integer. Okay. So we can do one thing. First, we can write n as a product of prime factors by fundamental theorem. Then we know n square is a perfect cube. So what is the condition for being a perfect cube? We'll check. N cube is a perfect square. What is the condition for being a perfect square? We'll check. But we need both. So we'll combine the condition. So if we combine the condition and then we start finding the smallest n, that is the procedure. So we can write. Now let's say n is equal to p1 alpha 1, p2 alpha 2, p3 alpha 3 and goes on. p1, p2, p3 are distinct and goes on, and alpha 1, alpha 2, alpha 3 are positive integer exponents, positive integral exponents. Okay, this two part is done. Now what next? So first condition is n square is a perfect cube. Okay, n square is perfect cube. So this was step 1, this step 2. N square is perfect cube. So what is the condition for perfect cube? I can say exponents need to be multiples of 3. What does this mean? See here, for example, if I write n is equal to 2 cube, so this will be perfect cube. Why? Because there are 3 multiples of 2. But यहाँ पे it's not n. We are talking of n square. So we are talking of n square. So if I write n square, so we can say p1 alpha 1, p2 alpha 2 and goes on somewhere, say pk alpha k. Then if I square it, so it will become p1 2 alpha 1, p2 2 alpha 2 and this goes on pk 2 alpha k. So, and this must be perfect square. So sorry, this must be perfect cube. So for n square to be perfect cube, what do we need? We need 2 alpha 1, 2 alpha 2 and this goes on, must be multiple of 3. That is the only way out. If I don't choose a multiple of 3, what is the meaning of perfect cube? We are taking one out of triplets. So if I can't form the triplet, how can it be a perfect cube? So for being a perfect cube, what do we need? The basic condition is be a multiple of 3. That is what is required. So first thing, this 2 alpha I multiple of 3. Then 2 is not multiple of 3. So 2 is not multiple of 3. But alpha 1, alpha I can say must be multiple of 3. Done. Now let's analyze the third part and then we can combine the equation. So they say n cube must be perfect square. So must be perfect square. Now how do we do it? So when does number is a perfect square? So a number is perfect square. So when is a number perfect square? A number is a perfect square when there are multiples of 2. When exponents are multiples of 3 or 2, it will be multiples of 2. For example, I can say again, n is equal to 36, say. So this will be 6 square. So this is perfect. It means the power must be multiples of 2. Now n cube can be written as p1 3 alpha 1, p2 3 alpha 2. Why I am cubing this? I am cubing the original equation. This was somewhere n. So I am cubing it. So if I cube it, power of 3 will add to each exponents. So p3 3 alpha 3 and this goes on. So n cube is perfect square means what 3 alpha 1 must be perfect square, must be perfect square, must be perfect square. Done. So if 3 alpha 1 is perfect square, then 3 alpha 1 must be multiple of, need not write necessarily 2 times, so I can write direct 3 alpha 1 must be multiple of 2, multiple of 2. Now 3 doesn't divide 2, so this concludes alpha 1 must be multiple of 2, multiple of 2. Now think of one thing, if I combine both, so this is fourth step. What? Combine both. If I combine both, alpha I must be multiple of 3 and 2 both, must be multiple of 3 and 2 both, that is LCM of 3 2, which is equal to what? 6. So it means alpha I, each alpha I must be multiple of 6, must be multiple of 6. Superb. Now this is the analyzation. If this is analyzed, what can be done now? Now we are looking, what we are looking for. We got what shall be the minimum value of the exponent, but n be a positive integer and greater than 1, so smallest positive integer. So it means if I take n greater than 1, the smallest positive integer is what? So smallest prime number for the base of base, या ऐसे लिखते हैं, smallest prime number for base is what? That is p1 is equal to 2. Then and alpha I is equal to 6, so therefore n is equal to 2 to the power 6, which is 64. So 64 and that is the answer. क्यों? n स्क्वायर जब करेंगे तो कितना हो जाएगा? 2 to the power 12, परफेक्ट क्यूब है, and n cube means 2 to the power 18, so multiple of 2, so perfect square, done. Superb, a good question. So this will become 64. Amazing. Now next question says, say find smallest positive integer n, such that product of its positive divisors is n to the power 10. Now how do we proceed? तो सबसे पहले इसमें क्या कर सकते हैं कि पहले मान लेते हैं कि नंबर ऑफ डिवाइसेस कुछ होगा, ठीक है. सो बेसिकली लेट n इज इक्वल टू d1 d2 कहाँ तक dk, जो कि k हम बोल रहे हैं, k इज टोटल नंबर ऑफ डिवाइसेस. किसके डिवाइसेस? तो मैं बात कर रहा हूँ d1 d2 d3 के लिए. और एंड p इज द प्रोडक्ट, मतलब इसका पॉजिटिव डिवाइसेस, मतलब ऐसे मान लो लेट n हैज, इसको ऐसे लिखो, प्रोडक्ट नहीं लिखते हैं, लेट n हैज पॉजिटिव डिवाइसेस d1 d2 d3 dk, और p मान लेते हैं, p इज द प्रोडक्ट ऑफ डिवाइसेस. ऐसा करते हैं कि p मान लेते हैं प्रोडक्ट ऑफ डिवाइसेस है इसका, ठीक है. सो p इज इक्वल टू d1 इंटू d2 इंटू d3, ऐसा चलता रहा टिल dk, ठीक है. सो अब हमें चाहिए क्या? हमें चाहिए कि फाइंड स्मॉलेस्ट पॉजिटिव इंटीजर n सच दैट प्रोडक्ट ऑफ इट्स पॉजिटिव डिवाइसेस इज n टू द पावर 10. मतलब एक सबसे छोटा इंटीजर पॉजिटिव n, ताकि जो उसके पॉजिटिव डिवाइसेस हों वो n टू द पावर 10 आ जाए. अच्छा, मतलब d1 d2 d3 अगर हम मल्टीप्लाई करें p जो हो जाए वो n टू द पावर 10 के बराबर हो जाए. तो बेसिकली हम कर क्या सकते हैं कि यहाँ पे एक बात तो हमको ये पता है कि if d divides n, so how it can be written? If d is a divisor of n, अगर d n का डिवाइजर है तो इसका मतलब देन n by d is also a divisor of n. ये तो ट्रू है, n by d is also a divisor of n. अब हम ऐसा क्यों बोले? जस्ट इसका मतलब क्या करो, डिवाइजर्स ऑफ n ट्राई टू ब्रिंग इन टू पेयर्स, ट्राई देम इन पेयर्स. अब ऐसा क्यों, अभी खुद पता चल जाएगा. जैसे मान लो क्यों पेयर कर रहे हैं. n अगर परफेक्ट स्क्वायर नहीं है, नॉट अ परफेक्ट स्क्वायर, तो इसका मतलब क्या होगा, इसके सारे डिवाइजर्स, ऑल डिवाइजर्स कैन बी पेयर्ड परफेक्टली. कैसे? चेक इट आउट. कैन बी पेयर्ड परफेक्टली. सो व्हाट इज द स्ट्रेटेजी कि कितने ऐसे पेयर्स होंगे. अगर मान लो k डिवाइजर्स हैं, तो पेयर कितने होंगे, k by 2 पेयर्स. जैसे एक एग्जांपल देते हैं, समझ में आएगा. जैसे मान लो 10 है. क्या 10 परफेक्ट स्क्वायर है? 10 नॉट ए परफेक्ट स्क्वायर. सो नॉट ए परफेक्ट स्क्वायर, तो इसका मतलब क्या हो जाएगा कि इसके डिवाइजर्स क्या क्या है, 1 2 5 10 डिवाइजर्स हैं. अब हम इसको पेयर अप क्यों किए, थोड़ा सा ध्यान देना. 10 इंटू 1 क्या होगा, 1 10 को एक पेयर मानो, 2 5 को एक पेयर मानो. सो दिस विल बी 10 इंटू 1 एंड 2 इंटू 5. सो बेसिकली दिस विल बी 10 का स्क्वायर. हो गया डिवाइजर्स का प्रोडक्ट. समझ में आया कैसे कर, पेयर अप ऐसे ही करना है. देखो n मैंने 10 लिया तो यहाँ पे क्या आया, 10 स्क्वायर आया. ठीक है, और हमें क्या चाहिए, अगर हम n लिए हैं तो प्रोडक्ट ऑफ पॉजिटिव डिवाइजर्स n टू द पावर 10 आने चाहिए. अगर n टू द पावर 2 रहता तब तो काम हो ही गया था. अब n को मान लेते हैं परफेक्ट स्क्वायर. तो परफेक्ट स्क्वायर जब मानेंगे तो इसका मतलब क्या हो जाएगा, 1 डिवाइजर, इसमें जो एक डिवाइजर होगा दैट इज रूट n, वो अपने से पेयर होगा. पेयर्स अप विथ इटसेल्फ. ये तो ट्रू है, पेयर्स अप विथ इटसेल्फ. एंड सेकेंड क्या हो जाएगा, ऑल अदर k minus 1 डिवाइजर्स form pairs. So this will form pairs. So therefore product कितना हो जाएगा, so product will be, what is the product, d1 d2 अगर करते चलें तो कितना हो जाएगा प्रोडक्ट. सो n पर पावर k माइनस 1/2 इतने पेयर्स बने, k माइनस 1/2 इंटू रूट n, ये एक पेयर था. सो दिस विल बी k माइनस 1/2. सो अगेन इट विल बी n टू द पावर k/2. सो n टू द पावर k/2. देखो यहाँ पे तो यही हुआ था कि अगर k डिवाइजर्स थे, सो दिस वॉज अगेन n पर पावर k/2, और यहाँ पे n पर पावर k/2. सुपर. इसका मतलब ऑलवेज द प्रोडक्ट ऑफ द डिवाइजर्स p is equal to n per power k/2, where k is equal to number of divisors. Now this is also a statement which you can remember always, कि product of divisors p is always equal to n to the power k/2, and k is what? K is the number of divisors. Superb. Now what is our statement? According to the question, we have been given p is equal to, which is n to the power k/2 is equal to n to the power 10. So therefore if we compare the exponents, k/2 will be equal to 10, which signifies k is equal to 20. So smallest positive integer n has exactly 20 divisors. मतलब what we are required to find? We are required to find smallest integer n which has perfectly 20 divisors. Superb. So what will be step third? This was C. First, what was the step? This was step 1. We found out the perfect square. What was step 2? We compared it. And what is step 3? So basically we are required to find number of divisors, matlab we are required to find smallest integer with how many divisors? With 20 divisors. So we are required to find smallest integer with 20 divisors. So how would we find it out? So n is equal to p1 alpha 1, p2 alpha 2. This is the way n is written. How? Fundamental theorem of arithmetic. Now, so number of divisors, which is k, which is 20 here, which is 20 here, can be written as alpha 1 plus 1 into alpha 2 plus 2, sorry, alpha 2 plus 1 into alpha 3 plus 1. How we are going about this? How did we find out the number of divisors? Remember, suppose it is 2 square into 3 square. So we said 2 0 is also one divisor, 2 1, 2 per power 2. So there are 3 divisors. So that's why if there is alpha exponent, then alpha plus 1 is the number of divisors for each prime. Okay, so now 20 can be written as, so how 20 can be written as? So first 20 can be written as 20, matlab that is 20 into 1. So basically 20 into 1, or 20 can be written as 10 into 2. It can also be written as 5 into 4. It can also be written as 5 into 2 into 2. Okay. So now and to make n smallest, we'll choose largest exponents for smallest primes, okay? Then only we can make it minimum for smallest primes, that is 2, 3, 5 and goes on. So say case 1, say it's 20. So if k is equal to 20, that is the number of divisors which is 20. इसको let's say suppose this as k is equal to यहाँ पे 20 हो रहा है, तो k if 20, then alpha 1 plus 1 is equal to 20, which is alpha 1 is equal to 19. Now smallest prime कौन सा है? 2, तो n कितना होना चाहिए? 2 to the power 19. Why? Smallest prime, choose smallest prime is 2, इसीलिए I have taken this. Now case 2. So this was case 1. Now case 2 is 10 into 2. So k can be written as alpha 1 plus 1, alpha 2 plus 1, which is equal to 10 into 2. So alpha 1 will be 9, alpha 2 will be equal to 1. So which one to choose smallest and which one to choose largest? So choose 2 per power 9, 3 per power 1. So this will be 500, 2 to the power 9 is 512 into 3. So this will be 1536. Again, for case third, it was 5 into 4. So this is 5 into 4. Again, which can be written as k is equal to alpha 1 plus 1 into alpha 2 plus 1. That is equal to 5 into 4. So therefore, alpha 1 is equal to 4 and alpha 2 is equal to 3. Again, choose smallest primes. So 2 per power 4 into 3 per power 3. So this is 16 into 27, which is equal to 432. Superb. Case 4, and I think this was the last case, 5 into 2 into 2. So for the last case, it is 5 into 2 into 2. So therefore, k will be equal to alpha 1 plus 1, alpha 2 plus 1 and alpha 3 plus 1, which is alpha 1 will be equal to 5. So alpha 1 is 4, alpha 2 is equal to 1 and alpha 3 is equal to 1 by comparison. So now n will be what? 2 per power 4, 3 per power 1, 5 per power 1. Done. So 2 to the power 4 is 16 into 3 into 5. So this will be equal to 240. Now which is the smallest one? So smallest one seems 240. Why? Because it was 432, it was 1536 and this is actually a very bigger number. So the smallest one is 240. So answer is smallest positive divisor, smallest positive integer n such that product of its divisors is n to the power 10 is equal to 240. Amazing question. Superb. What was the case? How we did it? First, we tried to put the number of devices in terms of pairs. What we find out, we concluded one thing. If p is the product of divisors, p is always equal to n to the power k by 2, where k is the number of divisors and what is n? N is the actual number which is given. Then in step 2 we find out what is k equal to. In third, we saw a smallest integer with 20 divisors, which is 240, and that is the answer. Amazing. It's a very nice question. So answer is 240. Done. Next. So next question says, now this is done. Next question says, let n is equal to 20 factorial. Find largest integer k, such that 2 to the power k is a divisor of n. It's very simple. Why? We have already studied Legendre's theorem. So if we know Legendre's formula, we can directly say Legendre's formula. How to find exponent of prime p in prime factorization of n factorial. Prime factorization of n factorial has a very simple formula, and it is given by exponent of prime p in n factorial is equal to n by p plus n by p square plus n by p cube plus it goes on. Okay, so if I put 2, how do we find it? Now here n is 20 factorial. N is 20, so n is 20 and p is what? 2. So let's start. P is 2. So let's start finding exponent of 2 in 20 factorial is given by 20 by 2 plus 20 by 2 square plus 20 by 2 cube plus 20 by 2 to the power 4 plus 20 by 2 to the power 5, and this goes on. 20 power 2 to the power, this goes on. Now we know this is what GIF, greatest integer function. So this is greatest integer function. Now 20 by 2 is what? 10. 20 by 2 square 4, it's 5. 20 by 2 cube, it's 2 plus 20 by 2 to the power 4, it will be 1. Why? I have already taught you GIF. What is GIF? GIF is the integer that is equal to or less than n, that is left of n. For example, I say you 7.5, its GIF will be 7. But if it is minus 7.5, it is minus 8. Why? Greatest integer less than or equal to x. It means if it is minus 7.5, so which is the nearest integer left to that of minus 7.5? It is minus 8, not minus 7. So that's why this is the answer. Now, so here we approximate and then it will be 0 for the rest of the things. So what is the value? 17, this is 18. So it means 2 to the power 18 divides 20 factorial, and that is the largest value. So k is equal to what? 18. Done. So this was easy. Next question says, find number of ordered pairs of positive integers x comma y that satisfy the equation 1 by x plus 1 by y is equal to 1 by 72. डन. सॉल्यूशन पार्ट के लिए खुद सोचो, ये तो x ग्रेटर देन 0 है, y ग्रेटर देन 0 है, तो इसका मतलब हम क्या कर सकते हैं? इसको मैनिपुलेट तो हम कर सकते हैं. मतलब आई कैन टेक एलसीएम. सो इफ आई टेक एलसीएम, so what it will look like? It will look like 72x plus 72y is equal to xy. So basically this can also be written as xy minus 72x minus 72y is equal to 0, which I can further manipulate. यहाँ से x बाहर निकालते हैं, कितना बचा? y minus 72. तो यहाँ भी हम 72 निकालते हैं बाहर, 72 आई कैन राइट, सो इट विल बिकम y माइनस 72, सेम चीज लाना है। लेकिन इसमें मैंने क्या किया, इसमें मैंने ऐड किया 72 स्क्वायर इस साइड, तो इस साइड भी करते हैं 72 स्क्वायर। सो बेसिकली दिस विल टर्न आउट टू बी x माइनस 72 इंटू वाई माइनस 72 दैट इज इक्वल टू 72 स्क्वायर। मैनिपुलेशन डन, बेसिक फैक्टराइजेशन था, ठीक है। ये फैक्टराइजेशन मैं पढ़ा भी रखा हूँ, आप देख लेना। साइमन्स फेवरेट फैक्टरिंग थ्योरम SFFT, पूरा विस्तृत लेक्चर है, ऑल द ओलंपियाड क्वेश्चंस आर कवर्ड, यू कैन जस्ट वॉच इट ओवर फ्रॉम देयर। सो x माइनस 72 इंटू वाई माइनस 72 इज इक्वल टू 72 स्क्वायर। नाउ एवरीथिंग इज पॉजिटिव हियर, ठीक है। सो इट मस्ट बी लाइक दिस, मस्ट बी पॉजिटिव, मस्ट बी पॉजिटिव, मस्ट बी पॉजिटिव, ठीक है। एवरीथिंग इज इन शॉर्ट। नाउ इसको लेट्स से दिस एज a, this as b, so a into b is equal to 72 square, that is given. So think of this way, say if 72 square has some positive divisor, has positive divisor, say d, so we can say if a is equal to d, if a is equal to d, then b will be equal to what, 72 square divided by d. So this is unique, so ab gives unique solution, gives unique solution for xy, gives unique solution for xy. So basically what we are, why x is what, if x minus 72 is equal to a, so x is equal to a plus 72 and y is equal to b plus 72. So if we find a b, we can find xy. Then it's very simple that number of solutions will be equal to what, is equal to number of positive divisors of 72 square, positive divisors of 72 squares. So what is the number of positive divisors of 72 square? Acha, why it is like that? See, a into b is 72 square, so if a is 72, b is also equal to 72. Now if a is 36, b is 144, again it will give you 72 ka square, so that's why. So number of positive divisors of 72 square. Now 72 square can be written as 36 into 2, that is 2 ka cube into 3 ka square per power 2, which is equal to 2 to the power 6 into 3 to the power 4. So therefore number of divisors is written as 7 choice for this, 7 choices into 5. So 7 into 5 choices, that is equal to 35, and hence there are 35 divisors which will give 35 pair of solutions. So answer is 35. Superb, but easy. So this is 35 pair. Next question says, question number, next one, find the last non-zero digit of 20 factorial. Last non-zero digit of 20 factorial. Now how do we find this? This may be tough. So now what's the procedure? How do we proceed this? 20 factorial is formed how? It is written as 2 square into 5. That is the prime factorization of this. And how do we find the last non-zero digit? Basically, see, last non-zero digit in terms of mathematics, last non-zero digit of a number will be given how? For example, if I write 2000, written 2000, which is the last non-zero digit, so this is 2. Okay, so if it is 2, how do we find this? If I say 2000 divided by 10 ka cube, then we can find out 2. So basically what I am writing, last non-zero digit of a number n is equal to n by 10 to the power k, which is mod 10. So there is k is number of trailing zeros. Trailing zeros means after the first non-zero digit number, how many zeros are there? That is known as trailing zeros. So this is trailing zeros of n. Done. Now how do we find the number of trailing zeros? So we can find Basically, this is the question. We have to find k. K means finding the number of trailing zeros. Say this is step 1. So step 2, what does step 2 imply? Step 2 implies find number of trailing zeros. Number of trailing zeros. So how do we find this? We have to find 10, that is equal to 2 into 5 ka power. Now exponent of 5 in 20 factorial. I am not finding 2 factorial. Can you tell me why? See, we need 2 into 5. The exponent of 5 will decide number of zeros, not 2 here, not 2. Why? If 2, say if 2 is power 10 and 5 is power 2, so how many tens can be made? 2 to the power 8 into 5 into 2 to the power 2. That is the way. So 2 to the power 8 into 10 ka square. So only 2 zeros can be made. So what decides the number of trailing zeros? The exponent of 5 in this case. I am saying in this case. If it was written divided by 2 to the power 9, then 2 would have decided the factors. Matlab, if it was like this, 2 to the power 10 into 5 to the power 5 to the power 2 divided by 2 to the power 9, then this is 2. So only one trailing zeros, 10 into 5. So which decides the factor now? 2. So basically in this case, exponents of 5 decide the number of zeros, trailing zeros. So how to find the exponent? 20 by 5 plus 20 by 5 ka square, and this goes on. So basically this will be 0 and this will be 4. So what can we write? 4 trailing zeros. So k is equal to 4. So 4 trailing zeros. 4 trailing zeros. Done. Now what is step 3? Step 3, we also find exponents of 2. So find exponent of other prime 2. Why? Because there is only one left. What is 20 factorial? 20 factorial is written as 2 ka power and 5 ka power. So basically what we are finding 2 ka power and 5 ka power. That will decide the exponents. That will decide the last non-zero digit. So basically exponent of 2 in 20 factorial can be written as 20 by 2 plus 20 by 2 ka square, that is 20 by 4, plus 20 by 8 plus 20 by 16 plus 20 by 32, that will be 0. So this is 10, this is 5, this is 2, this is 1. So total this will be 18. Now so 20 factorial can be written as 2 to the power 18 into 5 to the power 4, and I am only interested in this one. Let there be other primes. I don't have any consideration for other primes. Done. So basically, how to find the last digit? So finding, now we will be discussing only about the last step, that is finding last digit. Find the last digit. So how do we find it? We can say what we were required to find. N is equal to n by n to the power k, last non-zero digit of a number. So let this be x. So find the last digit. Let x is equal to what? 20 factorial. What was there? N by 10 to the power k. So 20 factorial, I am talking of 20 factorial divided by 10 to the power k is 4. Mod 10, that is what we need to find out. Mod 10. Done. Now, so 20 factorial is 2 to the power 18 into 5 to the power 4. There are some other primes divided by 2 to the power 4 into 5 to the power 4. So what does other prime means? It means from 1 to 20, but 2 and 5 removed. Now how do we calculate this? So basically this becomes, so therefore x is equal to, this gets cancelled. So 2 to the power 14 into some product of primes which is odd, product of odd primes mod 10. So how do we do it? Now suppose 2 to the power 14 and mod 10. So let's find 2 to the power 14. So what is 2 to the power 14 mod 10? How do we find it? So 2, what is the cyclicity of 2? What do we mean by cyclicity? See here, 2 ka power 1 is 2, 2 ka power 2 is 4, 2 ka power 3 is 8, 2 ka power 4 is 16 and 2 ka power 5 is 32. Can't you see that 2 gets repeated after 4 cycles? So cyclicity of 2 is 4. So what we can say that 2 to the power 14 has the same cyclicity, has the same unit digit as that of 2 to the power 2 mod 10, which is, matlab you write like this, instead of writing like this we can say 2 to the power 14 has same last digit as 2 to the power 4 into 3 plus 2, that is equal to 2 to the power 2, which is 4. So basically, therefore we can say 2 to the power 14 can be written as 2 to the power 2, that is 4 mod 10. Done. Now for product of p odd primes, so this will be 1, then again 3, 5 is removed, 7, then 9, then 11, because all 2's are removed. So here it will be 13, it will be 17, it will be 19. Now you will say me, sir, why 18 is not taken? 18 is not a prime. So p of odd primes I am taking. So 11, 13, 17, 19. Done. Now, so basically, how do we proceed with this? 1379 is there. Again, see here, very easy. We are required to find mod 10. So when 11 is divided by 10, again it will become 1, it will become 3, it will become 7, it will become 9. Super. So 1379. Now this can be written as again, see here, 9 square 81. So better way to count is, this will become again 7321. So this again when divided by 10 becomes 1. So 1 into 9, and here it will be again 7321. So 1 into 9, that is 81, and 81, so 81 will be conjugate modulo 1 mod 10. So basically all odd will have remainder 1 when divided by 10. So when we combine we get last digit d is equal to 2 to the power 14 p odd modulo 10, which is equal to 4 into 1, that is equal to 4 mod 10. So what is the last non-zero digit? So last non-zero digit of 10 factorial, sorry, of 20 factorial is equal to 4. Superb, amazing question. So now we know how do we find the last non-zero digit. So last non-zero digit of 20 factorial is 4. 4 is the answer. Done. Next question says, question is, let tau of n, this tau of n denote the number of positive divisors of an integer n. Find the smallest integer n that satisfies the equation tau of n plus tau of n plus 1 plus tau of n plus 2, and that is equal to 10. So how do we do this? So for the solution part, what does tau n indicates? This indicates the number of positive divisors of an integer. For example, tau of 1, it will be equal to 1. Why? Because 1 has only one factors. So tau of n, suppose I can say it is equal to 2. When? If and only if n is prime. Why? Let's take an example. For example, if I say tau of 7, that will be equal to 2. Why? It has only two factors, 1 and 7. But if I take any other number, for example tau of 3, again it will be 2, but tau of 4, it will not be equal to 2. Why? Because it is composite number. So it has 1, 2 and 5. So this will be 3. Why? There are 3 factors, 1, 2 and 4. Done. So basically tau of n, again tau of n is equal to odd if and only if n is perfect, square. Now you can tell me why. Let's check with an example if I have written it correctly. For example, if I say tau of 49, let's say what are the divisors of 49? 1, 7 and again it will be 49. 1, 7, 49. So this will be 3. So it is always odd when n is a perfect square. Check out here, tau of 4, it's again 3. So what does this mean? It means if tau of n is equal to k, okay, so it can be built and choose smallest with largest exponents. Choose smallest primes with largest exponents. Okay, so we can make it like this. For example, if I say smallest n with tau of n equal to 4. For example, if it is like that, tau n is equal to 4. So how many divisors we need? Actually we need 4 divisors. So one thing can be done, either choose 2 of cube is equal to 8. How many divisors? 4 divisors. Kyun? 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. Again you can choose, you will say me, okay sir, it can be written as 2 into 3, that is equal to 6. Why? Again it has exponents 2 to the power 0, 2 to the power 1, 3 to the power 0, 3 to the power 1. So you choose 2 choice. So 2 into 2, that is equal to 4 choices. So but which one is smallest? So smallest one is 6. Smallest is 6. So please remember these things for the solution of the question. Understood? Again say this was step 1. So this is step 1 of the question. First, to understand what a question perspective is. Again, what are the second ideas that we can take? Step 2. Now there are 3 consecutive integers. Here in the question there are 3 consecutive, n plus 1, n plus 2. So n plus 1 and n plus 2. So it means what we can say, what we can conclude here, at least one is even. Now there are 3 consecutive integers. Exactly 1 is multiple of 3, okay, and again we can say 1 or 2 are even, at least, and then we can say 1 or 2 are even. Why? If n is odd, n plus 1 is even. If n is even, n plus 2 is again even. So remember, either 2 are even or 2 are odd, but minimum 1 is even and 1 is multiple of 3. Okay, so what we are required to do, let's say tau of n is equal to a, tau of n plus 1 is equal to b, and tau of n plus 2 is equal to c. What is our, according to question, a plus b plus c is equal to 10, and tau of k, remember, is always greater than equal to 1. For k is equal to 1 even, tau of k is 1, and tau of k is greater than equal to 2 for what? K greater than 1. For k greater than 1. And there is something known as smallest. Later on, find the smallest integer n. So remember, here what we are required to take, a, b and c must be small. So a, b and c must be small. Must be small. So this is very important. Now we are done with step 1, step 2. Let's carry on with the third step. Step 3. We can take the cases. So if we take case, let's see what can be the possible values that are accepted. So case 1. Case 1. Say one of the numbers is perfect square. Suppose perfect square. It means tau must be odd. Must be odd. Why? We already discussed this. If one of the number is perfect square, its tau value must be odd. Now sum of a plus b plus c is equal to 10, which is even. It means if tau must be odd, so there must be even number of odd terms. Even number of odd terms. Why? If there are 2 even and 1 odd, there will be a problem. 2 even makes even. Even plus odd is odd, which is not true here. So if tau is perfect square, so if one of the number is perfect square, it means there must be even number of odd terms. Done? So it means there must be 2 perfect squares. There must be 2 perfect squares. See how logically the conclusion will be. 2 perfect squares. Why? Because if there is another tau which is odd, it is always of the perfect square. But 2 perfect squares is generally not separated by 1 or 2 number. For example, say there is 0, 1 or 1, 4. But these are not separated by 1 or 2 numbers. We need positive integers. Okay, true. And what else is the case? If I choose 1 and 4, so b must be again tau of b must be 5, which is not possible. So this case is gone. This case will be gone. So therefore these two values are impossible. So now again we need 2 odd tau values. First we need 2 perfect squares again, or perfect squares that are consecutive is 0, 1. Okay, but we need positive integers. And what are the pair of perfect squares with a difference of 2? Is there any perfect square? See here, you understand one thing, there is tau of n plus 1 and n plus 2. So we need consecutive terms. It means if I choose 1, then I have to choose 3. But is it possible? Not possible, because we know no consecutive, no pair of perfect squares with a difference of 2 is possible. With a difference of 2 is possible. Is not it means it is not possible. Now, so only consecutive integers are perfect square, that is 0 and 1. Okay, but 0 cannot be taken because we need positive integers. 0 is not an element of z plus, so this case is discarded. This case is discarded. So it's not possible. Okay, so let's check out again. So finalizing what we are saying, n plus 1 and n plus 2 containing 2 perfect squares. And 0 not allowed, or n greater than 1 Is not possible. Is not possible. Why? Because we are saying either y square minus x square is equal to 1. It means 0 wala case not acceptable, or y square minus x square is equal to 2. No integer solutions. No integer. Done. So it means there is nothing. There is no perfect squares. So none of n plus 1 n plus 2 can be perfect square. Can be a perfect square. They cannot be. Okay. Done. It means there is a very logical conclusion. It means tau of n plus 1 and tau of n plus 2 must all be even. Must all be even integers. Must all be even integers. Done. So what are the possible sets for this even integers? It means, let's see the possibility. We need to bring a plus b plus c is equal to 10 and all of them are even. So we can say 2, 2, 6. We can say 2, 4, 4. Are there any other possibilities? We'll check out. We'll check all the possibilities here. But first let's test. Any other case for 10. If I say 4, 4, 2, this is already done. If I say 6, 6, not possible. So these are the only two possibilities, 2, 2, 6 and 2, 4, 4. Superb. So we say for set 1. So let's see. This was step 3 now. Yeah, step 3. So step 4, let's test the cases. Step 4, we say 2, 2, 6. Start taking the cases. Now, say, what do we need? We need 2 consecutive primes. 2 consecutive primes. Why? Why 2 consecutive primes? In the beginning, already in step 1, I said that if there are 2 factors, it means n and n plus 1 both must be prime. So there is only one case. There is only one case 2 consecutive primes. And which are they? 2 and 3. 2 and 3. So it means we can say here n plus 1 are primes. It means n is equal to 2, n plus 1 is equal to 3. So therefore the triplets will be 2, 3, 4. Let's check the value. Tau of 2 is 2, superb. Tau of 3 is 2, superb. But tau of 4, that is 2 chi square, that is equal to 2 chi square. So it is 3. But 2 plus 2 plus 2, 2 plus 2 plus 3 is 7, not 10. So this doesn't work. Actually 4 was a perfect square, and initially I said you if no perfect square can be taken. So this case don't work at all. Now we can choose another thing. What? Let's say you will say ki sir, n plus 1 choose 2, n plus 2 choose 3. So basically n is equal to what? 1. So sir, the triplet will be 1, 2, 3. Choose like this. But let's see, tau of 1 is 1, tau of 2 is 2, tau of 3 is 2. Now a plus b plus c, so 2 plus 2 plus 1 is 5, not 10. False. Again, no cases. It means the set of tau values cannot be 2, 2 and 6. This is not possible. Okay. So basically not possible. Now, so what is the remaining possibility? Remaining possibility is what? 2, 2, 2, 4, 4, I guess, where it was written 2, 4, 4. So we'll see the next possibility, 2, 4, 4. So let's check out the set. First set taken is 2, 2, 6. Second set is 2, 4, 4. Okay. Now this is 2. So it means one number must be prime. One number must be prime. Superb. If one number is prime, then another must be a multiple of 3. One number must be prime, then one must be multiple of 3. Why? Because we are talking of consecutive integers, no? So 1 must be multiple of 3. multiple of 3. Now if multiple of 3 is prime, it means if both the condition are held by one number only. So if multiple of 3 is prime, it is equal to 3 only. It is 3 only. It is 3 only. But have we checked the cases of 3? We have already taken the cases of 3. So it means tau values were not coming same. If we have taken the case of 3, the values are not coming. So basically leave aside this case. So leave it. So for testing the values, we have already checked 1, 2, 3. We have checked 2, 3, 4. Now can we check 3, 4, 5? So if n was 1, so what was the value coming? 1, 2, 3. And the number of integers were coming 1, 2, 2. So it was 5. Sum 5. Not possible. N is equal to 2 if I am taking 2, 3, 4. So what is the number of divisors? I am talking of number of divisors. So for 2 it is 2 here, 3, 2 here, 4, 3. So sum is 7. Again not possible. For n is equal to 3. So what is the value? 3, 4, 5. So again there is 2, there is 3, there is 2. So sum is 7. Leave aside the case. Now n is equal to 4. So if n is equal to 4, then there is 4, 5, 6. Let's check out the case. For 4 there are 3 possibilities. For 5 there are 2 possibilities. For 6, 1, 2, 3 and 6, 4. So 4 to 6 sum is 9. Again not a possibility. So if I check n is equal to 5, let's see, 5, 6, 7. Again number of divisors for 5, 2, 6. There will be 1, 2, 3 and 6, 4, 7, 2. So sum is 8. Wrong. Now for n is equal to 6, it is 6, 7, 8. So for 6, how many divisors? 4, 7, 2. What is the number for 8? Again 4. Wow, superb. Sum is 10. It means we have found a triplet. We have found a triplet. Tau of 6. So tau of 6. Tau of 6. What is the value? That can be written as tau of 2 into 3. That is 1 plus 1 and 1 into 1 plus 1. Okay, superb. 4 divisors. And tau of 7 was 2 divisors and tau of 8 was again 4 divisors. Superb. This is matching our target. And that is what we required. The minimum integer. So the minimum integer, that the value that's coming through is 6. So what is the answer? The smallest integer, n is 6. Where's the question? The question says, let tau of n denote the number of positive integers, find the smallest integer n. So tau of n. So therefore n is equal to 6. Amazing question. Amazing. And that ends the lecture on fundamental theorem of arithmetic. Thank you, bachcho.